Now, for the rest of this lecture, I'm going to do something that I don't usually do. I don't feel comfortable with, and that is I'm going to teach by analogy. It turns out that teaching by analogy is not a really effective way of teaching, but it is a quick way of teaching, a quick and dirty way of teaching. And so I'm going to save some time by doing that here. We've been studying the linear motion of the center of mass of an object. And in doing that, we found that the one rule that does more for us than any other is Newton's second law. That you can solve more problems with F net equals ma than any other equation. Okay? And we read this equation as a net force causes a mass to accelerate. Okay? Now, last day, we found that a net torque causes a mass to angularly accelerate. Okay? We found that if you had a net torque, that was proportional to, oh, this is awkward, the angular acceleration. This would be angular. Okay? And this is a vector. So torque, fish, fish. Now, the question is, do we have the same relationship for linear dynamics that we had for, let me say that again, because I messed it up. Do we have the same relationship for rotational dynamics that we had for linear dynamics? In other words, is this the equation that governs all of rotational dynamics? And the only thing that's a question in there, we know that if we double the net torque, we double the angular acceleration. And we know that these two are in the same direction. We established that last lecture. The question is, if I replace this proportionality with an equal sign, I have to put some constant in here. And the question is that constant the mass of the object? Well, to answer that question, I've got a demo that I call the Olympic event rotating rods. It would be more effective if I had you people in the room and I could ask for 2 volunteers, but that ain't gonna happen. What I have here are 2 rods that have exactly the same mass, meaning if I put them on a scale, they would weigh exactly the same thing. And the event is that we try to rotate these things as quickly as we can, okay? And you can see that my left hand is much stronger than my right hand, or appears so, because I'm able to rotate this red rod very quickly, whereas this blue rod is not rotating easily. Now, if I had 2 of you up here to volunteer, I would obviously bring up a football player and someone that was smaller and have them compete here. And what we would find is that whoever has the blue rod is going to be the loser, okay? And that's because even though these 2 rods have the same amount of mass, that mass isn't located in the same place. In the red rod that's easy to rotate, most of the mass is located right here in the center, close to the axis of rotation, so that it's easy to rotate. Whereas for this blue rod, most of the mass is out at the ends, far away from the axis of rotation, making it hard to rotate. Okay, so for the same torque on both of these, I get a large angular acceleration here, and I get a small angular acceleration there. What that tells me is that mass clearly cannot be the constant of proportionality there. They have the same mass, they should get the same angular acceleration for the same net torque, but they don't, okay? It turns out that instead of just the mass, we have this quantity that we call the moment of inertia. Now, moment sounds like time, but it also has a meaning in calculus that we're not going to go into here. Anyway, just accept that that's the name that people use for this over and over. But you see that it depends on the mass. The more massive something is, the harder it is to rotate it. But it also depends on the size of the object. And this constant, B, is different for every different shape, okay? And it kind of tells where the average location of the mass is in that object. For example, in a disk that's rotating about its center, like this constant B would be 1/2. For a wheel that had most of its mass on the outside, that constant would be 1. If I had a beach ball that was hollow, that would have a value of 2/5. If I had a billiard ball or a bowling ball that was solid, that value would be 2/3. I got those last two mixed up. No, the solid one's 2/5 and the hollow one is 2/3. Okay. Yes. Okay. Sorry about that. Anyway, these are just worthless pieces of information that are stuck in my head. You are not going to need to know those values for the final exam. I repeat, you will not need to know those values for the final exam. If ever in your lifetime you need to know what those values are for different shapes, that's what Google was made for. That's exactly what Google was made for. Okay? Now, let's look at the ramifications of that. Suppose that you go to the circus and there's a high wire act, and that high wire act has someone walking across a wire clear up in the sky. Well, if this acrobat is really good, he or she is up there on the wire doing this, okay? If they're not so good, they're up there with a long pole going across the wire. And if it's their first day on the job, they've got the long pole, and on the ends of those poles, each end of the pole, there will be heavy weights, okay? And that's like having training wheels on your first day, okay? Why is that? Well, with that pole, the longer I make the pole and the more mass I can get further away from the axis of rotation, the harder it is to rotate that pole about its center. The bigger its moment of inertia. If I make this big and I put all the mass far away. Now, if this pole doesn't want to rotate, then it becomes a very nice handy thing to hold on to, because it's like it's stapled to the sky. When I push on it, it just doesn't want to rotate. And so if I feel myself falling off to the left, I just kind of pull up on the pole and right myself. Or if I'm falling off to the right, I pull up on the pole and right myself. Again, it's like having training wheels. There might also be another act at that circus, and that's where they take a long pole and they put a chair on the top of it. And they put somebody's kid brother on that chair, and then the older brother takes that pole with the kid on the chair and balances it on his forehead. Okay? Now, the longer the pole, the scarier this looks. But the longer the pole, the easier it is to balance that kid brother. And that's because the further I can get the mass away from the axis of rotation, the bigger the moment of inertia, and hence the harder it is to rotate. Let me just demonstrate that. I've got this tennis ball filled with lead shot, so there's a lot of mass in here. And if I try to balance that on my finger with the mass close to the axis of rotation, that's going to give me a very small moment of inertia, which means for a little torque, I can get a big alpha, big angular acceleration. And if I try to balance it that way, I just can't. You know, it might be because I'm old, it might be because I'm senile, but I'm telling you it's because the moment of inertia is small. Now, if we put that mass further away from the axis of rotation, well, now, even I can do it, okay? Even I can do it, because now the moment of inertia is large, and it's going to take a large torque to get any kind of angular acceleration there. Okay, you're free to clap at home. I assume that's what you're doing right now.